Hello everyone, I'm Ilya, and in this talk I will present you a logical approach to weak memory. So this is a joint work of 3 research groups, and the talk comprises 2 main parts. First, I will present in a nutshell what weak memory is about, and I will show you how the dependencies between instructions influence the semantics of the behavior of programs. And in the second part, I will show you how to calculate dependencies using logical approach, and thus how to acquire semantics. Okay, so first let me remind you what weak memory is about. So what the setting of weak memory is. So assume that our programs have very simple syntax. So program is just a sequence of instructions where every instruction is either read from a memory to a local register or it's a write to the memory. For example, here we first write value 1 to a location in the memory X, and then we read from X to a local register R. And our goal is to define an algorithm that takes a program as an input and produces the behavior of this program as an output. And by behavior, we mean the result of this program. That is the final state of the registers. So in this setting, this task looks easy because we can just go step by step. We can execute the instructions step by step, and meanwhile we can maintain the current state of the registers and the current state of the memory, and then on each step we know exactly the value that we write to the memory and exactly the value that we read from the memory. And so as we maintain these states, the resulting states of the registers is our answer, is our behavior, and we can just return it. So it's very simple, but let us assume one more thing. Let's assume that the programs are concurrent, that, for example, let's add to our thread, let's add another thread that writes to the same memory location X concurrently. Well, then we have a problem because the first thread can read either 1 or 2 depending on whose write was the last one. So if the last one was the write of the first thread, then we read from X a value 1. Whereas if the last one was the write of the second thread, then we read 2. So in this way, our behavior becomes non-deterministic. And instead of a single behavior, we have a set or a list of behaviors. But our goal stays the same. We need to provide an algorithm that takes a program and gives us a list of all possible behaviors of this program, all possible results of this program. So it doesn't look challenging because we can just do the following. We can just go step by step, and we can on each step pick non-deterministically one thread, execute some instructions in this thread, and during this process we maintain the state of the registers for each thread, the state of the global memory, and the current program instruction pointer for each thread. And so on each step we execute one of the threads and update the corresponding information, increment the instruction pointer, and repeat this process over and over. So in some sense, these parallel executions can be considered as a single-threaded execution where we combine the instructions from different threads by interleaving, right? And when we combine them, we should also preserve the in-thread order. So yeah, this semantics, this model of execution is called sequentially consistent semantics, or sequential consistency, or just SC for sure. But okay, let's look at the behaviors from a different perspective. So notice that as soon as we fix the value that we read from memory, as soon as we fix who wrote the value that we read, our behavior becomes deterministic. So as soon as we fix this graph, as soon as we know who was the last whose value we read, we can restore the final state of all the registers. So, and let's just use this idea and let's just define the behavior as a graph, because as soon as we have a graph, we can restore the final state of the registers. So let's just say that our behavior is graph itself. So then we can define semantics in a slightly different manner. So instead of defining it operationally, like an algorithm that would go step by step, execute instructions, maintain registers, let's define it axiomatically. So let's do the following. Let's take our program P as an input and produce all possible graphs of this program. And then we look at these graphs and filter out consistent graphs. So we will have a special predicate called consistency predicate that just takes a graph and says whether this graph is good or not. And as soon as we define this consistency predicate, we define our semantics. For example, it turns out that for the sequential consistency semantics that I showed you on the previous slide, we can define it in the following way. We can define it in terms of graph. We can just forbid cycles on PO union RF edges, where RF are the edges that I showed you that go from right, that initializes, that wrote the value that we read. So RF goes from right to read, and it shows that for a read, it shows the right who wrote the value that we read. Basically, it sounds convoluted, but it's quite simple. And PO is just in thread order that must be preserved, as I mentioned. Okay, so and as soon as we don't have PO and RF cycles, this graph defines a correct sequential consistency execution. That is, by this graph, we can acquire a behavior, the resulting state of the registers, that can be explained by the model of sequential consistency. But the problem with the sequential consistency model is that it is too restrictive to reflect the real executions. So for example, look at the following program. The second thread passes the value from the source location Y to the target location X. So it passes it through the local register S. So we first read from the source location Y to S, and then we write this value to the target location X. And the first thread first reads the target location X and then initializes the source location Y with 1. Right? So, and the question is whether it is possible for the first thread to read 1 from the target location X. So it seems like no, because if we first execute the first thread, then we write the initial value from X, the initial value is 0, so it's not 1. Or if we first execute the second thread, for example, if we first execute the first instruction of the second thread, if we first read from Y, then it doesn't affect anything. So then we just read the same 0 from X. Or if we execute the second thread completely, then we just pass the initial value 0 from Y to X. And we read this 0 from X in the first thread. So, and it's also impossible in terms of graphs, because if you look at the graph that explains this behavior, it contains PO union RF cycle. Sorry. Right, so this behavior is forbidden by the consistency predicate of, this consistency predicate. It's not sequential consistent. But it turns out that this behavior is possible in reality. Why is it possible? Because compilers and processors are very smart. They can look at the first thread and notice, these instructions, they are independent of each other. So it might be, so let's swap them. Because for some reason we want to swap these instructions because they are independent, so swapping them, there's nothing wrong with swapping them. So, and as soon as we swap them, this behavior becomes possible because we can first initialize the initial, the source location y, then we pass this one from y to x in the second thread, and then we read this one from x. So, and yeah, this reading one from x becomes possible. But what was wrong with the sequential consistency? What assumption was wrong? The assumption that was wrong is that PO order is preserved. So when we said that PO union RF is acyclic, we meant that PO and RF respect some sort of total order time, and it looks quite. It seems true because like we cannot read the value written in the future, so RF must preserve time, and in the sequential consistency we execute instructions from one thread in this order, in the order of this thread. So PO should be also preserved, but in reality it's actually false. So we can execute the instructions from one thread in different order, not in the order of the thread. If these instructions are independent, but if they depend on each other, then we cannot swap them. So for example, look at the second thread. The value that we write to x depends on the value that we read from y. It's the same value, right? So in this sense, the writing instruction to x depends on the reading instruction to y. And thus we cannot swap them. So let's replace our consistency predicate. Let's amend it a little bit. So instead of forbidding PO union RF cycles, let's forbid DEP union RF cycles, where DEP are edges representing dependencies. And yeah, as soon as we forbid DEP union RF cycles, it's okay. So this execution is fine because there is no DEP union RF cycle, and thus reading one from X is possible. But the question is, so and this execution is approved by our new consistency predicate. But the question is, how do we define these dependencies? And it turns out that defining dependencies is a tricky task. So the dependencies that I just showed you are called data dependencies. But there are other types of dependencies. For example, control dependencies that represent, that are related to control flow of the program. For example, look at this program. We write 1 to y only if r equals 1, which is true only if we read 1 from x. So in this sense, the fact that we write 1 to y depends on the fact that we read 1 from x. And thus we have this dependency edge from the reading instruction to the writing instruction. But let's add the else branch. The else branch that does exactly the same, that writes 1 to y. Then you might think that there is also a dependency edge, but in fact, it's not true. Because, for example, compilers are very smart. They can look at this if then else, and they can say, the then branch is the same as the else branch. So why do you even need if? Why do you even need branching? So let's just get rid of this if and replace it with just write 1 to y. So this way, this program might be transformed to this program. And after that, these instructions can be swapped. So in fact, there is no dependency from this instruction to that instruction. And this is so-called fake dependency. So although from the syntax perspective, there is a dependency, but from the semantical perspective, there is no dependency. So the moral of this example is that dependencies cannot be tracked syntactically, but we must reason about them semantically. And in the second part of my talk, I will show you how we use logic to track dependencies, to calculate dependencies semantically. And yeah, that basically concludes the first part of my talk. If you have any questions so far, please ask. Okay, so if there are no questions, let's move on. Okay, so remember that our goal is to define defining the semantics, and semantics takes a program and produces a list of graphs, a list of executions, behaviors that we represent by graphs. So let's define the semantic compositionally. Or denotationally, in other words. For example, if our program is a single instruction that write an expression e to a location x, then we produce an infinite list of graphs where every graph is a singleton graph. And this singleton graph consists of one vertex, one node, and this node represents this write. So it says that we write an expression e to the location x, and the actual value that we wrote is v. Okay, and we do the same thing for reads. So semantics of a read is an infinite list of graphs, and each graph is a singleton graph represented by one node. That just represents this read. And if we have a parallel composition of two programs or a sequential composition of two programs, then we just interpret these programs separately, and for every pair of graphs, we just combine them using the graph level composition. So we combine them using the graph level parallel composition and graph level sequential composition, where graph level compositions are defined below. So what does it mean to compose graph parallelly? It means that we just unite these graphs, right? Just simply union of graphs. But if we compose graphs sequentially, then we not only unite the graphs, but we also should add the dependency edges from graph G1 to graph G2. So this is the only place in our semantics where we can add dependencies. So they must be added here. But the question is, how do we add dependencies? So let's just do it in all possible ways. Remember that we return a list of graphs, so we can just choose how we add dependencies non-deterministically. So let's just add them in all possible ways. And then we filter out graphs that don't have enough dependencies. So we just, in our consistency predicate, we just look at the graphs and we'll have like another axiom that says that graph has enough dependencies or not. And the question is, how do we define what it means to be sufficient, or what does it mean to have enough dependencies? So we should look at the graph and say that it has enough dependencies. So to do this, let's add some extra information to our graphs. So specifically, let's add a function kappa. And what it does, it equips every node in the graph with a formula. About the state of the memory and registers. And this formula is called precondition. And what it means, this formula should hold in the beginning of the execution to validate the vertex, to validate the node. So we equip every node with this formula, and we say that this node is valid if in the beginning of the execution this formula, this precondition holds. And to be valid means that this node has enough incoming dependencies. So, and what we add to our consistency predicate is we add the requirement that all the formulas, all the preconditions of the nodes are tautological. Okay, so how do we define these kappas? How do we define the preconditions? Let's do it along with our denotational semantics. So remember, when we interpret a write, we get a singleton graph with a single vertex, let's call it n, and let's define the kappa, the precondition of this vertex n, as E equals V. That is, we say that this write is valid if we wrote the value that we are saying we wrote, right? So if E equals V. And for reads, we do the following. So we also get a singleton graph, and the precondition of read is let it be always true. So this may not seem intuitive, but we just define it as true because roughly because we don't track dependencies to reads in this stage. So let's just preconditions of read be true. Okay, so and if we compose graphs parallelly, we don't add any dependencies. So let's just keep the old preconditions. So the precondition of the new graph, the preconditions of the new graph are the same as the preconditions of the old graph. So in some sense, we just unite the preconditions from G1 and G2 to form the preconditions of the new graph. Okay, so we just take the old preconditions. But the interesting moment is how do we define the preconditions for the sequential composition? Because this is the place where we need, where we actually add the dependencies. So we should define the preconditions in such a way that it enforces adding dependencies. So it will become clearer in a couple of slides. But okay, this is the most interesting thing. So remember that precondition validates vertex. So and the vertices of the sequential composition is just a union of vertices of G1 and G2. So if the vertex, if the node is from G1, let's just keep the old precondition. Let's just keep the precondition of G1. So roughly this is because remember that precondition is a formula that must hold in the beginning of the execution to validate the node. So in the beginning of the new execution, G1 semicolon G2 is the same as the beginning of the execution G1. So this is roughly why we can preserve the old precondition. But what should we do for the nodes from the second graph? We cannot just take kappa of G2 because kappa of G2 are formulae that hold before G2 to validate the nodes of G2. But we need to construct formulas that hold before G1 to validate node from G2. So how do we define the preconditions for the nodes from G2? We need to somehow transform the preconditions of G2 by looking at the graph G1. So to understand how we do that, let me digress a little bit. So let's consider for one slide, we'll just consider a bit different thing. So and it will help us to understand how the preconditions should be transformed. So notice that programs can be considered as something transforming state of the memory, right? So, and this idea chimes with Horrortriples. Horrortriple is just judgment about two states in one program. And this judgment says that if we execute the program and before the execution state is this one, then after the execution state is that one. And we represent states via formulae. Right? So, and what we need for our purposes is so-called weakest precondition. So weakest precondition for a program P of a postcondition psi is the formula that is enough and sufficient to hold before the execution of the program P in order that psi holds after the execution of P. So in other words, weakest precondition for program P of a postcondition psi is the weakest formula phi such that phi P psi is a Horrortriple. Right? For example, if the program doesn't modify memory at all, for example, if the program is just a read instruction, then formula psi holds after the execution of this program if and only if it held before the execution of this program, because psi describes the state of the memory and state of the memory stays the same. So yeah. But if our program modifies the memory, for example, if it's a write to a memory, then we should modify the postcondition. So for example, if we write an expression E to a memory location X, then psi holds after this instruction if and only if psi, where we replaced E for X, held before the execution of this instruction. Right? So, for example, if we apply this rule to our example, we have that weakest precondition of writing for writing 6 to X of formula X equals 6 is 6 equals 6. Yeah, so we replace X with 6 and get 6 equals 6, which is a tautology. And it means that no matter what state we start from after the execution of, after we write 6 to X, X equals 6 holds, which sounds reasonable. Okay, and what do we do with programs with sequential composition of two programs? Well, we need to take our postcondition, first apply the weakest precondition of P2, and then apply the weakest precondition of P1 to the result. So in other words, we transform the sequential composition of programs to the functional composition of weakest preconditions. Okay, so that was a digression. Let's come back to our goal. So we need to, let me remind you that we need to define kappas, our preconditions, for the case of sequential composition of two graphs, where we take a node from the second graph. So what should we do? We should take the precondition from G2 of this node and transform it by the weakest precondition of G1. So this is basically the intuition, right? This is a basic idea. However, there are some nuances. In fact, remember that not all the events of G1 are ordered before n. Only those events of G1 are ordered before n that are on which n depends. Oh, sorry. So if some events of G1 If n doesn't depend on some events of G1, then these events of G1 can be ordered after n. So, and these events that are independent of n, they can be, there's no order from them to n, and they shouldn't affect the transformation of the precondition. So this is the first thing. And the second thing is our kappas, our formulae, they are not only about the memory, they are also about the registers. So let's just use another notation. So let's not call it weakest precondition, let's call it tau. We call it predicate transformer. And predicate transformer for a graph is a family of function from formula to formula, and this family is indexed by a set of events, which is called dependent set. So, and what we do is we take the precondition from graph G2 and transform it by the predicate transformer of graph G1, indexed by the dependent set of n, indexed by the set of vertices that n depends on. Right? So, and this set is defined just the prefix of the dependency relation. Okay, and the point is that we will define this tau, we will define this predicate transformer in such a manner that the bigger this dependent set is, the stronger this transformer is, right? So remember that we need all kappas to be tautological. And as soon as we need it, we want this transformer to be strong enough to transform this precondition into a tautology. So, and in this sense, we need the set dn be big enough so that this thing is a tautology. And what it means, what does it mean for dn be big enough? It means that there are a lot of like incoming edges to our vertex n, to our node n. So this is the mechanism. This is how we enforce the dependency edges by requiring all the kappas be tautological. Okay, so let me show you how this tau, how these transformers are constructed. So this is what we already know. So when we interpret a single write, we get this infinite set of graphs for all possible values v. We have a graph of a single vertex called n, which represents this read. And for writing instructions, we do the same. And the precondition for reads are true, and for writes they are meaningful. They say that E equals V. And for sequential composition, we just take all pairs of graphs from semantics of P2 and semantics of P1 and semantics of P2, and all possible dependencies between these graphs. And the preconditions they depend on whether this node is from the new graph, from the second graph, or from the first graph. And if it's from the first graph, then it's just an old precondition. And if it's from the second graph, that it's an old precondition transformed by the transformer of the first graph. So that's what we already know. So let's add taus. Let's add our predicate transformers. So for sequential composition and for write, predicate transformers are almost the same as weakest precondition. So for sequential composition, it's just a functional composition of predicate transformers of G1 and G2. And for write instruction, the predicate transformer just gets a formula and substitutes X for V in this formula. But for reads, we do something different. For reads, the transformer depends on this set D. the dependency set D. So if this reading event N belongs to the set D, then we know that the precondition that we transform by this transformer is the precondition of a write that depends on this read, right? So if N belongs to D, then this transformer should be strong because we have this dependency edge, right? So and then it's what this transformer does is so it adds the premise that R equals V to our precondition psi. But if N doesn't belong to D, if D doesn't contain N, then it means that this transformer is applied to a precondition of a write that doesn't depend on this read. So we can like reorder these reads and writes, and we shouldn't weaken this psi so much. So this transformer shouldn't be so strong. So instead of adding R equals V, we add some weaker premise that R equals V or R equals X. So this R equals X should not be intuitive. So in fact, we needed for like another compiler optimization. But the point is that the premise is weaker here than here because here we don't want this transformer to be strong because we don't have the dependency. Okay. So, and that's it. We say that the graph is consistent only if there are no dependency union RF cycles in this graph, and all the kappas for all the vertices are tautological. So in some sense, this requirement gives us an upper bound for dependencies, because if we have too much dependencies, that we can form a depth union RF cycle, right? And this requirement gives us a lower bound for dependencies, because if we don't have enough dependencies, then we don't have enough strong transformers, right? And as we don't have enough strong transformers, they don't transform the preconditions to tautologies, right? So yeah, but we require that all the preconditions are tautologies. So this is the intuition behind this intuition of how we enforce dependency edges. And let me show you a couple of examples to make it simpler. Okay, so let's just assume that our program is just to read from a memory location Y to a local register R. Then one of the graphs from our semantics is a singleton graph that just contains the information about this read, and it says that we read value 1. And the predicate transformer of this graph, because it's a read, it depends on the set D. So if D contains this read, then the predicate transformer just add the premise S equals 1. And if D doesn't contain this read, then the predicate transformer adds a weaker premise that S equals 1 or S equals Y. Okay, so this is just semantics of S equals Y, of read from Y to S. Okay, so let's look at the write instruction. When we write S to a location X. Okay, so we also get an infinite set of graphs, but one of these graphs is a singleton graph that says that we write 1 from S to X. So let's call this instruction B. And the precondition of this write is that says that S equals 1. Right? So remember that preconditions for read are just true. And preconditions for write say that s equals this value. So this value is 1. Okay, so but now let's compose these instructions sequentially. And let's look at the semantics of this program. So it consists of two events, A and B. And let's look at the precondition of B in this graph, in the new graph. So what should it be? It is the precondition of B in the old graph, that is s equals 1, transformed by the predicate transformer of the first graph, the predicate transformer of A, right? Indexed by the dependent set of B. So in other words, the precondition of B depends on whether or not A is in the dependent set of B, or whether or not there is dependency H from A to B. And if there is a dependency H, then we transform s equals 1 by adding premise s equals 1. And those we get a tautology, and that's okay. But if there is no H from A to B, then we transform s equals 1 by adding premise s equals 1 or s equals y. And this is not a tautology. So if there is no H from A to B, kappa of B is not a tautology, and our consistency predicate rejects this graph because it requires all the kappas be tautological. So this is how we deal with data dependencies. So if we add this, if the graph contains this dependency edge, then it's okay. If it doesn't contain that, it's rejected by the consistency predicate. So let me show you how we deal with control dependencies. I won't go into details because I didn't show you how we define semantics for ifs, but okay, let's look at this example. We have the second instruction under the condition that r equals 1. And the precondition of this instruction is 1 equals 1. But since it's under the condition that r equals 1, we also transform it by adding r equals 1. And so the precondition is r equals 1 and 1 equals 1. Why this precondition? So remember that precondition sort of validate the node. So this node is valid only if r equals 1. So that's why we add this r equals 1. But then we transform this precondition by the transformer of the first instruction. That is the same as the transformer from a previous slide. And it adds r equals 1 as a premise. So if there is an edge, and if there is no edge, it adds something different. So, and what I want to say is that this formula is equivalent to r equals 1. And so it is required for B to be dependent on A, for B to depend on A. So this edge from A to B is required because we want this kappa to be tautological. So it's basically similar to the previous example. So to transform r equals 1 into tautology, we need to add r equals 1 as a premise. Okay, but if we have an else branch, then this, I didn't show you, but in fact, these two instructions can be represented by a single event in our graph. And this event, B, it sort of collects the preconditions from both branches. So it's not just r equals 1 and 1 equals 1, but it's r equals 1 and 1 equals 1, or r is not equal to 1 and 1 equals 1. So we just combine the condition from if and condition from else. And this way, if you look closely at the formula, you can notice that it's just a tautology, right? And since it's a tautology, we don't need any premise to make it tautology. So we don't care if we add r equals 1 or if we add r equals x as a premise. It will be tautology anyway. So in this sense, we don't force this edge from A to B. And even if there is no edge from A to B, our consistency predicate says that this is okay, because yeah, the precondition is tautological. Okay, so that's how we deal with control dependencies and fake control dependencies. And that's basically it. So to conclude, I showed you an oversimplified version of the model that we proposed, and this model is called POM sets with predicate transformers. POM set just means graphs, and or PWT for short. And in this model, we apply logic to calculate dependencies. And a nice feature of this model is its compositionality. So instead of defining the semantics of adding the instruction to the end of the program, we define the semantics of a proper sequential composition, right? And it has a lot of benefits. For example, now we can prove that prove the correctness of some compiler optimizations. For example, if we prove that two instructions can be swapped, if semantics of P1, P2 equals to semantics of P2, P1, then this property is true in any context, right? So in any program, and yeah, so we can prove such properties easier. And this is, so to say, a core model that has two real quote-unquote implementations. So first one is PWT-C11, which is a model for C programming language, and it forbids so-called out of thin air behaviors, but at the same moment it allows some compiler optimizations. And another implementation is called PWT-MCA, which is designed for multi-copy atomic systems. And it supports an optimal compilation to ARM. This model was also formalized in COC, and we proved some essential properties of this model, for example, associativity of Semicolon. And currently we are proving the correctness of compilation of this model to IMM. And also our colleagues from the University of Kent developed a tool called Pewter. It is an automatic evaluator of this model. So it takes a program as an input and produces all the execution allowed by these models as an output. And this work will be presented on POPL 22. Okay, so that's basically it. If you have any questions, feel free to ask.
I have a couple of questions.
Yeah.
The first one is how scalable is this method? So you mentioned two concrete weak memory models like C11 and C8, and how can you evaluate the scalability? Because there are a lot of other weak memory models. Will this approach fit for all of them?
Yeah, that's a good question. I think we are like the next paper will be like regarding this model will be about some other implementation of this model. If Anton is here, he would answer it better, but I think we'll also apply it to.
Thank you.
Yeah.
So I had some glitches at the question. So if I properly understand it, the question was how scalable the model, how it could cover other weak memory models, right?
Yeah.
Okay. So first of all, I need to say that to show that this model is scalable or good enough, it should be weaker than hardware memory models. So yeah, essentially this is what we are going to show by proving compilation to IMM, since IMM compiles optimally to ARM, Power, and x86. Is it answering a question if it's possible to use the same approach, let's say in promising semantics? I would say no, because it's like an alternative approach to forbid out-of-linear executions.
Okay, thank you.
Thank you.
Yeah, you have some hands rising as far as Mr. Nikolaev is asking a question, right?
Okay, thank you. Very naive question. Because basically you introduce quite complicated graph compositions, very natural is to consider, instead of just graphs, some colored Petri nets with well, conditions for colors, something like this. Maybe it will be much more transparent and easier to understand. In particular, honestly, not about quality of presentation. Of course, I failed to track all details. Okay, thank you. Naive question, but what do you think on this topic?
Yeah, I think Petri nets can be employed here, but yeah, I'm not an expert in Petri nets. I have no experience with them, so it's. But yeah, from what I heard, I think it can be put in Petri nets as well. Like, but it can be put in graphs. So it's
okay. Okay.
Yeah.
Yeah, I guess the main point here is that we don't actually use just normal graphs, but we use event structures instead in this work. So it already covers like some, I mean, combines many graphs in one structure.
Yeah. Yeah, so this is like what I showed you is like oversimplification of the model. So in fact, it's a bit more complicated.
I have another question. As far as I understood from the presentation, it's maybe you just have taken a shortcut, but you deal with assignments and parallel sequential compositions. What about loops, jumps, etc.?
Loops, as far as I understand, loops are not covered by this model, and this is like a point of future work, I suppose. But yeah, we also deal with ifs, and yeah, also with.
Yes. Question. I also have a question considering loops. So is this model really truly compositional? So my question is, where in fact, you define not the predicate transformer using the text of the program, but instead you somehow define the family of predicate transformer using the dependencies. So where those dependencies come from? I think I missed this moment.
Okay, so this is like the main point. So our goal is to define dependency. Our goal is to define what it means for dependencies to be enough. So we just say that. So where was it? Okay, I think it's here. So okay, when we define the whole like set of graphs, we compose graphs in with all possible dependencies. Like. And since it's all possible ways we add dependencies, somewhere in this set there are good graphs, and then we filter out the graphs.
You somehow enumerate all possible graphs, do you?
Yeah, in some sense. I mean, we take all pairs of graphs from P1 and P2 and add all the possible dependencies between them. So it's it's a finite set, but it's a large set. But this is just a representation. I don't think that in paper we used exactly this this syntax for putting it.
Yeah, I see. In fact, it is possible to deal with some over approximations. In fact, to support loops, you need to talk about the weakest preconditions, not precise weakest preconditions, but instead some over approximations of those conditions. Yeah. Possible to do with these dependencies.
Yeah, I think it is possible.
I mean, over approximation. Calculate or essentially introduce more dependencies, 6 points in the semantics, and yeah, this is future work.
Sorry, I think I had some network connection issue. I missed your answer, Anton.
I mean, I said that over approximation should be fine because essentially we could, for example, assume that
I presume that the problem is on Anton's side.
Each read event use to each write event, and that would be some.
Yeah, I've missed the second part again. I don't know, is it my issue or your issue, but yeah, I think we can talk a bit later. Thank you.
Yeah.
Other questions, comments, suggestions, topics for discussion?
Well,
yes, please.
Just a comment. I'm not pretending for final truth or something like this. It looks very much like test-driven approach. So basically, what you are able to do, you just are able to resolve some problems with one particular example. What is the outmost purpose? What is challenge in this case?
Yeah, okay, so I think that...
So, sorry, please don't accept it as an offense. Your talk was indeed very good.
Yeah, thank you. But yeah, I think the reason why you think that it's like test-driven approach is because of my talk, because I showed you only one example, but or like two examples. And in fact, the oversimplification of the model may not be true for all the cases. It only serves as an illustration of the main idea. But what we do is we formalize this model in Coq, which allows us to prove that it's not just about like some examples, and we prove some global properties of this model. And so the next goal is to prove the compilation correctness, which is not at all about like single examples. That's a global property that says that this model is good enough. So, but yeah, the oversimplification that I showed you is about test-driven development.
Okay, thank you. It is just a comment, nothing else.
Mm-hmm. Thank you.
Okay, more comments, questions, suggestions? Nope. Yeah, thank you for your presentation. It was nice to see you again.
Yeah, thank you.
I hope you're doing great in Cambridge. And,
yeah,
we all wish you all the best there, and hope this is not our last encounter. So.
Yeah, I hope to participate in the seminar later as well.
Yeah. Thank you. Bye-bye.
Yeah,
Thank you, everyone.
Bye.